Imagine you are doing the impossible. You are standing atop the tallest mountain in the universe, looking down at all of creation sprawled at your feet. Galaxies glitter like dust in the rays of a cosmic dawn. All of it, stars, planets, life, history, seems eternal, unshakable, fundamental. But what if that foundation is an illusion? What if the very fabric of reality, the space in which those galaxies float, is unreliable? Unstable? What if everything we see, everything we are, exists in a state of cosmic lottery where the winning ticket hasn't been drawn, and the losing one means absolute, total, instant oblivion? This is not a science fiction plot. It is a strict, mathematically sound prediction of modern physics. It stems from our most accurate and successful theories describing reality at its deepest level. And it has a cold, unemotional name: vacuum decay. What is it? The simplest way to think of our universe is not as emptiness, but as a field. A vast, invisible energy field permeating every cubic centimeter of space. This is the so-called Higgs field, which gives mass to elementary particles. But what if this field is not in the lowest, most stable energy state? What if it is stuck in a metastable dimple, like a ball that has rolled into a small depression on the slope of a giant mountain? The ball seems stable. It could lie there for billions of years. But it is not at the bottom. Not in the true minimum. And it takes just a small nudge, a quantum fluctuation, a high-energy particle, a strange event, for that ball to roll out of its dimple and tumble down into the true, absolute abyss. When that happens, and physics tells us it is possible, the catastrophe will be total and irreversible. The point where this new, true vacuum is born will become the epicenter of a spherical bubble that will expand in all directions at the speed of light. Its walls are the front of absolute transformation of the laws of physics. Everything they touch will cease to exist in any familiar sense. Atoms will disintegrate, forces will stop working, space and time will warp beyond recognition. This is not an explosion. It is a quiet, clean, perfect erasure of the old reality and its replacement with a new, alien one, where our concepts of matter, energy, and life have no meaning. Our universe is 13.8 billion years old. In all that time, vacuum decay has not occurred. Or has it? Can we be sure? What if everything we thought about the stability and eternity of our reality is wrong? What if we live in a fragile, temporary bubble of cosmic stability, beyond which an alien physics rages, and this bubble could pop at any moment, without warning? Today we embark on a journey through the evidence and calculations that challenge everything we hold as immutable. We will descend to the quantum level to understand the nature of this threat. We will trace the history of the universe to find traces of possible past catastrophes. We will ask the most frightening question: could this catastrophe be triggered artificially? And we will try to find out if we are all sleeping on a powder keg of fundamental physics. Get ready. We begin. So, we have asked the frightening question. But where did this insane idea come from in the first place? To understand that, we need to travel to a not-so-distant past, to a place where the boldest theories about the foundation of reality were born. In 2012, the world of physics rejoiced. At the Large Hadron Collider at CERN, the discovery of the last missing piece of the Standard Model, the Higgs boson, was announced. It was a victory of human intellect. The particle responsible for the mass of all things had been caught. The picture of the world seemed almost complete. But within this triumph lay the seed of deep unease. To understand why, let's understand what the scientists actually discovered. The Higgs boson is not just a mass particle. It is a manifestation, a ripple on the surface of an invisible ocean that permeates the entire universe. That ocean, the Higgs field. Imagine all of space filled with something like incredibly thick, invisible honey. Particles moving through it interact with this stickiness and acquire what we perceive as inertial mass. The stronger the interaction, the heavier the particle. An electron barely grazes this field, while a top quark literally gets bogged down in it. The Higgs boson is a quantum of this field, its smallest possible excitation. But here is the key: this field, this cosmic honey, has a certain energy level. It wants to be in the state with the lowest possible energy, like a ball that has rolled to the bottom of a bowl. This state is called the true vacuum, absolutely stable, unchanging, final. However, calculations based on the measured properties of the newly found Higgs boson, especially its mass, began to yield an alarming result. They indicated that the Higgs field, which defines so much in our world, might not be in the lowest energy state. It is stuck in a metastable state. Let's return to our analogy, but make it more precise. Imagine not a bowl, but a complex landscape with hills and valleys. Our universe is a ball that is stuck not in the deepest valley, but on a small ledge on the slope of a giant mountain. This ledge is a local depression. The ball is relatively comfortable here, it could remain here for billions of years. It has even created a whole complex universe around itself. But much further down, there is a real, global valley with incomparably lower energy. That is the true vacuum. And the physical law is inexorable, everything in the universe tends toward the state of minimum energy. Our position is one of frozen tension. Who noticed this and when? The very concept of a false vacuum was discussed as early as the 1970s by physicists like Sidney Coleman. But those were abstract, speculative constructs. Everything changed with precise data from the LHC. In 2013 to 2014, after processing the results, groups of theorists worldwide, including teams from Harvard, MIT, and Italy's Gran Sasso, began to sound the alarm. Their calculations showed, within the Standard Model, extrapolating its behavior to incredibly high energies, our Higgs field, with a probability close to 100%, is in a metastable state. The false depression in which we live is not eternal. The initial reaction of the scientific community was a mix of skepticism and horror. Skepticism, because these calculations relied on extrapolating our knowledge into areas where it might no longer be valid. Horror, because if they are correct, the threat is fundamental. This is not an asteroid, not a supernova flare. It is a change of the very rules of the game. Some scientists rush to declare it merely an artifact of an incomplete theory, that new physics, such as dark matter or supersymmetry, would necessarily stabilize the vacuum. But as collider data became more precise, and the expected new physics failed to appear, the picture did not change. On the contrary, it became clearer and clearer in a disturbing direction. The central mystery, the paradox facing physicists, sounded like this: if our vacuum is so fragile and unstable, why has the universe already lasted 13.8 billion years? Over such a colossal time, any quantum fluctuation, any rarest high-energy process could have triggered a catastrophe. We should have observed bubbles of true vacuum expanding from ancient, early epochs. But we don't see them. Does that mean we are wrong? Or have we just been incredibly, fantastically lucky? But the accumulated data pushes us toward an unpleasant thought: our luck is not an accident. Perhaps it is a consequence of how this cosmic trap is precisely constructed. And to realize this, we need to leave the cozy world of known particles and descend into the boiling, chaotic abyss of the quantum world, where the concepts of empty and full lose all meaning. So, our Higgs field, according to calculations, is in a precarious, metastable state. But how did scientists even come to this conclusion? This is not reading tea leaves. It is the result of colossal work, ultra-precise measurements, and data collected from the cutting edge of science. Let's imagine a giant mathematical model of our universe based on the Standard Model of particle physics. This model is like a complex map of mountainous terrain, where every peak and depression describes the energy state of fields. Two parameters are key to determining the shape of this landscape in the region of the Higgs field: the mass of the Higgs boson and the mass of the top quark, the heaviest known elementary particle. Their ratio is the coordinates that indicate where exactly our ball is in the universe. In 2012, when the Higgs boson was discovered, its mass was measured at approximately 125 gigaelectronvolts, GeV. This value itself was the first warning bell. It fell within a rather narrow, dangerous range. If the Higgs mass were slightly higher, say 130 GeV, calculations show our false depression would be much deeper and more stable. If slightly lower, 115 GeV, we might already be in the true vacuum. But 125 GeV is a value that places us on the edge, on the slope. But the Higgs alone is not enough. A second player is needed, the top quark. Its mass, measured with incredible precision, is about 172.5 GeV. The top quark, due to its monstrous mass, exerts a colossal influence on the Higgs field. It seems to pull it downward, toward lower energy levels. Together, these two numbers are fed into the equations. What do the equations say? They show that when extrapolating the behavior of fields to mind-boggling energies close to the so-called Planck energy, 10 to 19 GeV, the energy at which quantum gravity effects operate, our landscape changes catastrophically. The false depression in which we sit disappears. It simply ceases to be a minimum. And this means that at such energies, our vacuum is absolutely unstable. It should have immediately rolled down. But we exist. So, is there some barrier protecting us? Exactly. And this barrier is created by quantum corrections. Imagine that on the mountainside where our ball lies, dense bushes have grown. They temporarily hold the ball from falling. In our model, these bushes are virtual particles constantly being born and annihilating in the quantum foam of the vacuum. They distort the energy landscape, creating that very local dimple in which we live. But this dimple is shallow. Calculations show that the energy barrier separating us from the abyss of the true vacuum is relatively low. And the bottom of the true vacuum lies at a monstrously, incalculably low energy level. The difference in energy between our state and the true vacuum is that colossal force that, in the event of a transition, will unleash the apocalypse. What is the scale of the threat? The energy released during the transition of 1 cubic centimeter of our vacuum into the true one, according to some estimates, could exceed the energy released by the annihilation of all visible matter in the Milky Way galaxy. But this is not just an explosion. It is a rewriting of the laws of physics. Inside the bubble of the new vacuum, concepts like nucleus, atom, star may cease to exist. Perhaps even space will acquire a different dimensionality, and time will flow differently or stop altogether. Classical explanations trying to save stability fail one after another. Supersymmetry? It predicted a whole zoo of new particles at LHC energies, which were never detected. New physics at the TeV scale? The collider doesn't see it. More and more data indicates that we live in a very special, very unstable point in the space of all possible universes. But this is just a small fragment of a much stranger picture. Because the metastability of the Higgs field is not a verdict, but a condition of the problem. The question is how the transition can occur? And here we leave the solid ground of measurements and plunge into the ghostly world of quantum probability, where the impossible becomes inevitable if you wait long enough. And the key to this is a phenomenon that sounds like magic but is a cornerstone of modern physics, quantum tunneling. So, we have come to the very edge. We are prisoners of a false energy well, held on a slope by a fragile barrier of quantum fields. It would seem that if there is a barrier, we are safe. But in the quantum world, the concept of a barrier loses its absolute meaning. Here, the most ghostly and powerful mechanism comes into play, allowing the impossible to happen, quantum tunneling. Imagine that very ball in the dimple on the mountainside. From a classical, Newtonian point of view, for it to roll down into the true valley, it first needs to rise above the edge of its dimple, to overcome the energy barrier. For this, it needs additional energy or a push. Without it, it will remain there forever. But quantum mechanics turns this logic on its head. From its point of view, the ball is not just a ball, but a blurred wave of probability. And there exists a non-zero, albeit vanishingly small, probability that this ball will suddenly find itself on the other side of the barrier, not overcoming it in the classical sense, but as if seeping through it, like a ghost through a wall. It makes a tunnel transition. This is exactly what could happen to our vacuum. At some point in space, as a result of a purely random quantum fluctuation, the Higgs field could locally tunnel through the energy barrier and end up in the state of the true vacuum. This point will become the seed of catastrophe, the nucleus of a bubble of new reality. Now, the key question, when can this happen? And here we encounter the first paradox linking the quantum world to cosmological scales. The lifetime of a metastable state is calculated according to the laws of quantum field theory. And the calculations for our universe yield a staggering result. The probability of such an event in any given cubic centimeter of space over a time equal to the age of the universe is incredibly, astronomically small. So small that it's easier to express it as 1 chance in a number that is greater than the number of all atoms in the observable universe raised to the 10th power. It would seem we can breathe a sigh of relief. The threat exists, but it is practically zero. But physics is inexorable. Practically does not mean absolutely. Moreover, in an infinite or just sufficiently large universe, even an incredibly small probability becomes inevitability. If you have an infinite number of cubic centimeters of space and an infinite amount of time, even the most improbable event must occur. And not just once. And here we approach the most shocking discovery of the last decade related to cosmology. Observations of the cosmic microwave background and the accelerated expansion of the universe have given us an understanding. Space beyond our cosmological horizon, the region we can observe, is most likely infinite and continues to expand exponentially due to dark energy. This means that out there, in depths inaccessible to our gaze, there exists an infinite amount of matter, stars, galaxies, and an infinite number of such false vacuums as ours. In infinity, everything that can happen, does happen. An infinite number of times. This means that right now, at an unimaginable distance, trillions of light years away from us, vacuum decay could have already occurred. And not just one. There may exist, or may have long existed, spherical fronts of new physics, inexorably creeping through the cosmos at the speed of light. They engulf entire worlds, rewriting the laws of being. And we cannot see them because the light from these events simply hasn't had time to reach us and may never reach us due to the accelerated expansion of space. But that's not all. Even in our own, observable universe, the probability is not zero. And it could be higher than we think. Because tunneling requires not just any fluctuation, but a fluctuation of a certain size and energy. And what if there are processes that can catalyze this event, sharply increasing its probability? What if the role of such a catalyst could be played by a black hole? Or a collision of particles at incredibly high energies? Or some exotic cosmic object? The deepest concerns of some theorists, such as the late Stephen Hawking, were connected precisely with this. Hawking considered a scenario in which a microscopic black hole, evaporating due to his own radiation, in the last moments of its life reaches temperatures and energies capable of triggering a phase transition of the vacuum in the surrounding space. This evidence and reasoning take us far beyond abstract field theory. They lead us to an existential question about the very nature of our reality. We are forced to ask: is our observed, seemingly stable universe just a local phenomenon in a vast, raging ocean of the multiverse, where different physical laws arise and perish in an endless cycle of vacuum decays? This thought is staggering. But it logically follows from the accumulated data. And it brings us to the threshold of a new, grand picture of the universe, where our fate depends on the finest balance of numbers in equations. We have come to the brink. Data and calculation suggest our world hangs by a thread of quantum probability in an infinite multiverse where vacuum decay catastrophes might be commonplace. But what if this is not a bug, but a feature? What if the very structure of reality is built this way, and our instability is the key to understanding everything? To piece together all these disturbing puzzles, we need to turn to the most ambitious and controversial theoretical construct of modern physics, the string theory landscape and the concept of eternal inflation. Let's start with a simple but radical conclusion: if our vacuum is metastable, then somewhere there exists, or can exist, a state of true, absolute minimum energy. And if so, why should we limit ourselves to only two states, ours and the true one? The mathematics of quantum field theory allows for the existence of a giant, perhaps unimaginably vast number of different stable and metastable vacua. Each of these vacua is a separate universe with its own unique laws of physics, values of constants, such as the strength of gravity or the electron charge, and even, possibly, a different number of spatial and temporal dimensions. This is precisely what string theory predicts. Within its framework, the landscape of possible vacua is not a metaphor but a mathematical reality. The number of such stable states is estimated by an astronomical figure, perhaps 10 to 500, a 1 followed by 500 zeros. This number is so large it exceeds the number of all elementary particles in the observable universe. Each of these states is a separate bubble of reality, its own universe. How do these bubbles arise? This is where the theory of cosmic inflation comes onto the stage. According to it, in the first fractions of a second after the Big Bang, space underwent a period of fantastically fast, exponential expansion. But what if inflation never completely stopped? What if it is an eternal property of some primordial field, the inflaton? The theory of eternal inflation, developed by physicists like Andret Linde and Alexander Vilenkin, asserts this is so. In this model, the primordial inflationary space, called the metaverse, expands faster than the speed of light. But locally, at different points, the inflaton field can randomly tunnel into one of the many low-energy states, those very vacua from the string theory landscape. When such tunneling occurs, a bubble of a new universe is born. Inside it, inflation stops, the field's energy transforms into matter and radiation, a local Big Bang happens. This bubble begins to expand within the metaverse, but its boundaries also move at nearly the speed of light. Meanwhile, the metaverse between the bubbles continues to inflate even faster. The result is an infinitely foaming, bubbling multiverse where new bubble universes are born forever, never filling all of space. Some of these bubbles are stable. Others, like ours possibly, are metastable and doomed to eventual decay. This grand picture is the overarching theory that explains everything we have seen. Our metastability, we are simply in one of the bubbles with at not the lowest of vacuum. We are not at the center of creation, we are one of countless experiments in the landscape of possible physics. The absence of observed decay bubbles, our bubble is young enough, 13.8 billion years, and within it, no catastrophic tunneling has occurred in that time. And bubbles from the outside simply haven't reached us yet due to colossal distances and the accelerated expansion of space. The fine-tuning of constants, why in our universe are the constants seemingly perfectly fine-tuned for the emergence of complex matter and life? The anthropic principle in the context of the multiverse provides a simple but staggering answer. Because only in such universes with such constants can an observer appear to ask this question. We are not in a special universe. We are in one of the few universes where such existence is even possible. The others are lifeless and empty. But this theory has alternatives and serious problems. Alternative 1, we are wrong. There is new physics beyond the standard model, e.g., dark matter particles, additional fields, that stabilizes our vacuum, making it the true minimum. This is the most desirable scenario for us, but, as already mentioned, evidence for such physics is still lacking. Alternative 2, more radical, the Hull hypothesis or Venn of geometry. Some theorists, like Nikodem Poplawski, suggest that collapse into a singularity inside a black hole is the birth of a new universe via wormhole formation. In this model, our universe could have been born from a black hole in a parent universe. And vacuum decay could be the mechanism of death for one universe and the birth of another, not through an infinite foam, but through a sequential chain. Problems with the landscape theory, it is incredibly difficult to test. Predictions that could be confirmed or refuted by observations are either absent or lie beyond our technical capabilities. Critics, like Nobel laureate David Gross, call it not science but postmodern speculation, as it can essentially explain anything without making specific predictions. But regardless of which theory is closer to the truth, the mere fact of serious discussion about vacuum decay forces us to reconsider the foundations. What is nothing? The vacuum is not emptiness, it is an active, quantum, energetically charged entity, the basis of being. What is reality? Perhaps it is just a local, temporary operating mode of some universal field that can be reset at any moment. What is the fate of the universe? We are faced not with the dark, cold expanse of heat death, but with the drama of quantum choice, where the end can come suddenly, from within the very fabric of space-time. This new picture assigns humanity a simultaneously humble and unique role. We are fragile, fleeting observers in one of the bubbles of consciousness, yet capable, by the power of our intellect, of comprehending the laws that may foretell the end of our world. And this leads us to the final, practical question: can we do something about it? Can we learn more, predict the threat, or even prevent it? We have encountered a theoretical abyss that calls into question the very foundation of our existence. But science is not only about building speculative castles. It is about the search for evidence. The question now is, can we somehow test this frightening theory? Can we detect signs of an impending vacuum decay or traces of other reality bubbles? The answer, surprisingly, is encouraging yes. And in the coming decades, we will have tools capable of either finding these traces or forever consigning the idea of our instability to the archive of scientific curiosities. Our first and main tool is the Large Hadron Collider, LHC, and its successors. Although the LHC most likely cannot directly trigger vacuum decay, this requires energies trillions of times higher. It performs a critically important task, refining the map of our position on the energy landscape. Each new, more precise measurement of the Higgs boson and top quark masses narrows the range of possible scenarios. Scientists at CERN and other laboratories worldwide, like the ATLAS and CMS collaborations, are literally gathering data bit by bit to understand how deep and wide our false well is. The next generation of accelerators is already on the drawing board. The Future Circular Collider, FCC, at CERN or the International Linear Collider, ILC, in Japan will be able to measure the properties of the Higgs boson with unprecedented, sub-percent accuracy. They will look for the tiniest deviations in its decays that could point to interaction with dark matter particles or traces of new fields capable of stabilizing the vacuum. If these deviations are found, we may discover the supports that keep our world in relative safety. But accelerators are only one side of the coin. The other side lies in space. If vacuum decay is happening somewhere in the multiverse, it must leave traces, albeit indirect ones. How? Imagine a bubble of true vacuum expanding in a sea of false vacuum. At the boundary between these two phases, the bubble wall, processes of monstrous energy release must occur. This wall could emit powerful gravitational waves, bursts of high-energy radiation, and perhaps even create strange, anisotropic patterns in the cosmic microwave background. It is precisely these scars that the newest observatories are targeting. The Euclid Space Observatory, which recently began operations, is mapping the structure of the universe and the distribution of dark matter with unprecedented accuracy. It could detect giant, inexplicable distortions in the large-scale structure of the cosmos, perhaps bruises left by the collision of our bubble with another in the distant past. Even more promising are next-generation gravitational wave detectors. The space-based antenna LISA, Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will catch low-frequency gravitational waves from cosmic-scale events. Mergers of supermassive black holes, oscillations of cosmic strings, and, possibly, vacuum phase transitions in the early universe. Calculations show that if our vacuum became metastable not immediately, but as a result of some transition in the first moments after the Big Bang, this process should have generated a gravitational wave background that LISA could detect. This would be the most direct hint that we live in a special phase of existence. Finally, the boldest and most direct search. What if we try to see the tunneling act itself? Not on universal scales, but in a laboratory? Experimental physicists, such as groups at the Niels Bohr Institute and MIT, propose using analogous systems, ultracold Bose-Einstein condensates, nanomagnets, or superconducting qubits. In these systems, one can artificially create a metastable state and observe its quantum decay via tunneling. By studying the statistics and dynamics of these decays under controlled conditions, we can extrapolate the laws to cosmological scales and obtain a more accurate estimate of our universe's lifetime. This is an area where quantum simulators and quantum computers could revolutionize, modeling quantum fields inaccessible to direct experiment. Recent breakthroughs in astrophysics already give us reason to expect surprises. The discovery of anomalies in B meson decays at the LHC, the so-called B anomalies, strange signals in data from the IceCube Neutrino Observatory. Each of these deviations from the standard model could be a crack through which a more fundamental landscape is glimpsed. Ultimately, all these efforts boil down to key questions for humanity. Are we alone in reality? Is our physics the only possible one? And most importantly, does our existence have a long-term future? The answers we may get in the next 20 to 30 years will have philosophical significance comparable to the Copernican revolution. We will either discover that we live in a fragile, unique, and doomed world, or find evidence of its deep, fundamental stability. But what if the worst-case scenario turns out to be true? What if we are truly trapped in a metastable vacuum? This brings us to the final, deepest, and most speculative act of our investigation, where we will ask questions science cannot yet answer, but which define the very boundary between physics and metaphysics. We have gathered the evidence, theories, and plans for future research. But the deepest conclusions emerge when we consider not just the mechanism of vacuum decay, but its place in the grand drama of reality. This is no longer a question about particles or fields, it is a question about meaning, time, and the very nature of existence. Rising to this level, we face questions that challenge not only our science but our perception of ourselves. The first ultimate question, what is a nothing, and how can it die? All our intuition tells us that emptiness is the ultimate limit, a state of complete absence of anything. But the physics of the 20th and 21st centuries has mercilessly destroyed this naive picture. The quantum vacuum is a boiling ocean of virtual particles, field fluctuations, and complex energy. It has properties, structure, and, as we have found out, can exist in different phases. Vacuum decay is not death from something external. It is death from internal metamorphosis. It is as if the very concept of possibility changed, making our existence not just impossible, but unthinkable within the new system of coordinates. This forces us to reconsider the very act of creation. The Big Bang could have been just such a phase transition of the vacuum from one state to another, the one we live in now. And our universe, in that case, is not everything, but merely an episode in the eternal evolution of a field of more fundamental reality. The second question, how does vacuum decay intertwine with other cosmic fates? For a long time, cosmology had two main scenarios for the end of everything: the Big Rip or heat death, a slow, dark, and cold fading into an expanding void. Vacuum decay introduces a third, radical option, the sudden collapse, which could negate all other scenarios at any moment. But what if they are connected? Some theorists, for example, Avi Loeb from Harvard, consider a shocking possibility: dark energy, causing the accelerated expansion of the universe, may not be a fundamental constant but a slowly changing field. And its evolution could gradually destabilize the Higgs field, eroding the walls of our false well. In this nightmarish yet elegant scenario, two processes go hand in hand: the universe expands, empties, cools, and as it expands, the probability of catastrophic quantum tunneling increases. Heat death would not be the finale, but merely the prelude to instant vanishing. Thus, the most remote and abstract end could be closely linked to quantum processes at every point in space. The third, most frightening question, can intelligence become the cause of its own demise? The Fermi paradox asks, where is everybody? If intelligent life is common, why don't we see its traces? One of the dark solutions to the paradox is the Great Filter, a stage of development that is almost impossible to overcome and that destroys civilizations. We always thought of nuclear war, asteroids, biotechnological catastrophes. But what if the greatest filter is reaching an energy level capable of triggering vacuum decay? Imagine a civilization that, over millions of years of development, learned to manipulate space-time, create wormholes, extract energy from the vacuum. In its experiment with the fundamental structure of reality, it might accidentally create conditions for tunneling, a microscopic black hole with wrong parameters, a clot of energy trillions of times more powerful than at the LHC, yet still negligible by cosmic standards. One failed experiment, and a bubble of death begins to grow in the laboratory, swallowing first the planet, then the star, then the galaxy. This would explain the sinister silence of the cosmos. The most advanced civilizations do not make contact because they destroyed not only themselves but their local patch of space-time. We, humanity, may be approaching this threshold. Our accelerators are safe for now, but who knows what will happen in 1,000 years? Based on these questions, we can outline not 2 to 4, but a whole spectrum of possible future scenarios, from the most optimistic to the apocalyptic. The stability scenario, optimistic: we are wrong. The new physics we will discover in the next 50 years, e.g., at the FCC or in underground dark matter detectors, will show that our vacuum is the true, absolute minimum. The multiverse landscape exists, but we are in its deepest and safest valley. The universe is doomed to heat death, but this will take trillions of years, giving intelligence unimaginable opportunities for development and, perhaps, escape to other universes via wormholes. The fragile equilibrium scenario, realistic our vacuum is metastable, but its lifetime is fantastically long, for example, 10 to 100 years. This is so much longer than the time to heat death that the threat has no practical significance. We live in bubbles that will last almost forever, but the theoretical possibility of an end remains. Civilizations of the future will know about this threat as we know about the possibility of a giant asteroid impact and may develop ways to monitor it or even reinforce the vacuum using advanced technology. The cosmic Russian roulette scenario, pessimistic the lifetime of our vacuum is comparable to the age of the universe or even shorter. We exist only due to incredible luck. At any moment, at any point in space, tunneling could occur, and we can do nothing about it. Moreover, the high energy associated with some astrophysical processes, supernova explosion, neutron star merger, evaporation of primordial black holes, could locally increase the probability of catastrophe. We live under a sword of Damocles held by a quantum thread. The active apocalypse scenario, techno-dark intelligence is not a passive victim but an active destroyer. Advanced civilizations, upon reaching a certain level, either perish as a result of experiments or, even more terrifying, use vacuum decay as a weapon. War on cosmic scales might look not like an exchange of nuclear missiles, but like the pinpoint ignition of the vacuum in an enemy's system, followed by the uncontrolled spread of a bubble of death. In that case, the Great Silence is the result of total xenoparanoia and mutual assured destruction on a galactic scale. These scenarios lead us to the climax of our journey. We started with a question about the stability of the Higgs field and arrived at questions about the meaning of the evolution of intelligence, the ethics of scientific knowledge, and the ultimate value of existence. Vacuum decay ceases to be just an exotic physical hypothesis. It becomes a prism through which we see our place in the cosmos in all its fragile, dramatic, and uncertain beauty. The next step is to complete this picture. To summarize everything we have learned and face what remains the greatest mystery. We must gather our courage and ask the final, all-encompassing question, what does all this mean for us, here and now? We have come a long way. From the first, alarming calculations after the discovery of the Higgs boson to the abyss of the multiverse, where reality foams and bubbles in an eternal dance of births and deaths. We have encountered evidence that leads us to one of the deepest and most frightening conclusions in the history of science: the foundation of our world may be temporary. Let's return to that provocative question we started with: what if everything we thought about the stability of our reality is wrong? Now we have an answer. And it is not unambiguous. It is not a loud yes or a reassuring no. Science rarely gives simple answers to ultimate questions. The answer we have today is a map of unknown territory, marking both paths to salvation and abysses. What have we learned? We have learned that nothing is not emptiness. The vacuum is a dynamic, quantum entity, a field of the highest complexity, on whose state everything depends: particles, forces, the very structure of space and time. We have learned that data from our best experiments indicate this field may be in a state of metastable equilibrium, like a ball on the slope of a giant mountain. We understood the mechanism of a possible catastrophe, quantum tunneling, capable at any moment and at any point of giving birth to a bubble of alien physics that will relentlessly consume everything. We saw how this threat weaves into the most modern cosmological theories, eternal inflation and the string theory landscape, painting a picture of an infinite multiverse where our universe is just one of myriad bubbles. And finally, we realized that the greatest mystery, instability, could be the key to explaining the very fine-tuning of the laws of nature and the sinister silence of the cosmos. What remains a mystery? Practically everything that matters. We do not know the exact lifetime of our vacuum. This number is stretched into such a giant range of probabilities that it loses practical meaning. We do not know if new physics exists that stabilizes our position. We do not know if dark energy is the slow poison eroding our walls. We do not know if such decays have happened before and if spherical fronts of absolute nothingness are wandering somewhere right now, at an unimaginable distance. And most importantly, we do not know if intelligence is the inevitable executioner of its own reality. Where is the scientific consensus today? It is cautious and restrained. Most physicists agree that within the current standard model, without considering gravity, the vacuum indeed appears metastable. This is not speculation but a result of calculations. However, no one is sounding the alarm. Why? Because everyone understands, these calculations extrapolate our knowledge into an area where it is almost certainly incomplete. Where quantum gravity, the theory of everything, must come into play. As long as we lack such a theory, all predictions about the fate of the vacuum remain preliminary. The consensus states, yes, there is an interesting and profound problem. No, there is no evidence that a catastrophe is imminent. Our understanding is too incomplete to draw far-reaching conclusions. We need to keep searching. And it is precisely in this search that our strength and our hope lie. The universe is immense. Its mysteries are infinite. And some of these mysteries concern the very foundation on which our world stands. The realization of this fragility should not paralyze us. On the contrary, it should inspire. It makes our existence, our ability to ask these questions and seek answers, an even more precious and astounding wonder. We are beings born in a metastable bubble of space and time, and we have managed to look beyond its limits. We, specks of dust on the edge of one of countless galaxies, have managed to comprehend the laws governing an entire multiverse and understand our place within it. This is a triumph of reason over scale, of curiosity over nothingness. The bubble of our reality may be fragile, but the candle of reason lit within it illuminates the darkness. And as long as it burns, as long as we ask questions, build theories, launch telescopes and colliders, we are not just passive inhabitants of this bubble. We are its consciousness. And our journey through its mysteries, through these abysses of the possible and the impossible, is only just beginning.